In this video, I would like to show you a few probability examples, but let's first start by reviewing some of the basic rules of probability. To start with, we should look at the definition of the probability of an outcome. The probability of outcome A, denoted P of A, is a number between 0 and 1 indicating the proportion of the time that outcome A occurs in the long run. So it is the likelihood of an event. One thing to note here is that all probabilities are between 0 and 1, with 0 meaning the outcome never occurs and 1 meaning the outcome is guaranteed to occur. Next, we'll take a look at complements. The complement of any outcome A is defined to be the event that outcome A does not occur, so it is all of the other possible outcomes except for A. We will use the complement rule to find the probability of a complement. Since all possible outcomes in a sample space together must have a probability of 1, it makes sense then that the probability of the complement of outcome A would be 1 minus the probability of A. So probability of not A is equal to 1 minus the probability of A. Moving on to some other probability rules, we first need to define disjoint outcomes. Two outcomes are disjoint if they cannot occur at the same time. An example would be drawing a 6 and drawing a king when I draw a single card from a standard deck of cards. The card that is drawn cannot possibly be both a 6 and a king at the same time. So drawing a 6 and drawing a king are disjoint outcomes. We know that the chance of both outcomes happening in a single draw is 0, but sometimes we might want to find the probability of one or the other outcome occurring. To do this, we'll use the addition rule for disjoint outcomes. It states that if A and B are two disjoint outcomes, meaning they cannot occur at the same time, then the probability that A or B occurs is the sum of the two individual probabilities. So the probability of A or B equals the probability of A plus the probability of B. Since there's no overlap between the two outcomes, we can just add up their individual probabilities to get the probability that one or the other occurs. Disjoint outcomes are often confused with independent outcomes. Two outcomes are independent if knowing that one outcome occurs does not change the probability that the other outcome occurs. So suppose I still consider the two outcomes we used before, drawing a 6 and drawing a king, but this time I'm going to draw one card, replace it, and then draw another card. In this case, drawing a 6 on the first draw and drawing a king second would be independent outcomes, because knowing that I drew a 6 first does not affect the probability of getting a king on the second draw, since I'm replacing the cards as I draw. To find the probability that both of these events occur, we use the multiplication rule for independent outcomes. If A and B are two independent outcomes, the probability that both outcomes occur is the probability of A and B, which is equal to the probability of A times the probability of B. So when we have two independent outcomes, we multiply their respective probabilities to find the probability that both outcomes occur. Let's move on to our first example. A study on the current marital status of women aged 25 to 29 years old was conducted on a large group of women between the ages of 25 and 29. The table below summarizes the findings of this study. What is the probability that a randomly selected woman aged 25 to 29 years old is currently either never married or divorced? So we need to find the probability that the woman selected has either never been married or is divorced. We'll call outcome 1 never married and outcome 2 divorced. Note that these are disjoint events because no woman can be both never married and divorced at the same time. Thus, we can use the addition rule for disjoint events. So the probability that the woman is either never married or divorced is equal to the sum of the two individual probabilities. Up here in the chart, we see that the probability that she has never been married is 0.468 and the probability that she is divorced is 0.06. We will add those two probabilities for a sum of 0.528. Therefore, if we randomly select a woman between the ages of 25 to 29 years old, there is a 0.528 chance that she has either never been married or is divorced. For our next example, we'll use the same information from the previous study, but this time two women aged 25 to 29 are randomly selected. What is the probability that the first woman has never been married and the second woman is divorced? Here's the probability we're asked to find. The probability that the first woman has never been married and the second woman is divorced. The two outcomes of interest are outcome 1, first woman has never been married, and outcome 2, second woman is divorced. Note that it is probably safe to assume that these outcomes are independent of each other because the women were randomly selected from the population. Therefore, we can use the multiplication rule for independent events. So, the probability that the first woman has never been married and the second woman is divorced is equal to the probability of never married times the probability of divorced. These are the same numbers as the last example, but this time, since we want to find the probability of both independent events occurring, we're going to multiply those numbers together. Multiply 0.468 and 0.06 for a product of 0.02808. So there's only about a 2.8% chance that the first woman selected has never been married and the second woman is divorced. Our next example has a different scenario. Suppose an automobile manufacturer buys computer chips from a supplier. Each chip chosen from this shipment has probability 0.05 of being defective. Each automobile uses 7 computer chips that are both selected independently and work independently of each other. What is the probability that all 7 chips in an automobile will work properly? So we're asked to find the probability that all 7 chips work properly. Let's define outcome 1 as chip 1 works properly, and similarly outcome 2 is that chip 2 works properly. Then we continue until we get to chip 7 works properly for outcome 7. So note that all 7 chips work properly is the same as chip 1 works and chip 2 works and chip 3 works all the way up to chip 7 works. We're given that each chip is selected and works independently of each other. Therefore, we can use the multiplication rule for independent events here. Note that the multiplication rule that was stated earlier in this video was only for 2 outcomes, but it can also be applied to multiple independent events like this. So the probability that all 7 chips work properly means that chip 1 works and chip 2 works all the way up to chip 7 works. Since all 7 of these outcomes are independent, using the multiplication rule, we multiply all 7 of the individual probabilities together. But what is the probability that any one of the chips works? In the problem up above here, it states that each chip chosen from this shipment has probability 0.05 of being defective. We don't want the probability that the chip is defective, we want the probability that it's not defective. So note that the probability that chip 1 works is equal to 1 minus the probability that chip 1 does not work, which is 1 minus 0.05 or 0.95. That's from the complement rule. This is the same for all 7 chips. So we're going to have 0.95 7 times here. That's 0.95 to the 7th power, which is 0.6983. Therefore, the chance that all 7 chips work properly is almost 0.7 or about 70%. In this last example, we will use the same computer chip scenario, but this time we're asked to find the probability that at least one of the 7 chips is defective. The event at least one chip is defective can happen a lot of different ways. For example, it's possible that there's only one defective chip. This could maybe be chip 1, or maybe it's chip 6 that's defective. Another possibility is that there could be exactly 2 defective chips. For example, maybe chips 1 and 5 are defective, or maybe chips 3 and 4 are defective. Or maybe there's 3 chips out of the 7 that are defective. Or maybe all 7 chips are defective. All of these scenarios satisfy the event at least one is defective. Hopefully you see that solving this problem with this approach could be quite tedious. Luckily, there's another way. So we don't want to try this approach here. Let's look at the event at least one chip is defective. At least one chip is defective is the complement or the opposite of none of the chips are defective. Therefore, the probability that at least one chip is defective is 1 minus the probability that none of the chips are defective. Right here, note that none of the chips are defective is just another way of saying all 7 chips work properly. Well, that's the probability that we solved for in the previous problem. It was 0.6983. So the probability that at least one chip is defective is 1 minus 0.6983 from the previous example, which is 0.3017. That was so much easier than adding up all of the individual probabilities that we first tried to do up here. So watch out for those complements. They can really come in handy.